Hello, everyone. Thank you for coming. I'm going to be talking about some of my research on inverse problems in nuclear engineering. And hopefully, as you can tell from my title and the picture there of a cargo ship, there's a lot of inverse problems to be solved looking for detecting nuclear materials. So before I move into my talk, I wanted to acknowledge my advisor, Dr. Azmi, and my two sort of unofficial advisors in some of the subject matters, Dr. Kukuch and Dr. Mattingly from the Department of Nuclear Engineering at NC State. So I really appreciate the CSGF conference, and this is probably an obvious analogy. And in case you can't read the license plate there, that is a Yugo license plate. But the reason I wanted to make this point was that the conference is really a great opportunity. So last year at the poster session, I was walking around, doing the mingling thing, and I stumbled upon James Martin's poster on Bayesian inference methods, and I'd been looking at a lot of different methods, but my interest was piqued there, and so that was an encouragement to me to pursue some of those methods more. And so if you see some similarities between this talk and his, you'll know why that is. Okay, so my main research is on locating sources. So for instance, maybe in a building, you have a bunch of radiation spread out, and you'd like to know where is that coming from. However, I'm going to hopefully zoom in on a smaller problem today that's a little more digestible for 15 minutes and talk about what happens if you have maybe a crate and you know from detector measurements that there's some type of nuclear materials in there, but you don't know, you can't open the crate. And so the question is, what's in there and how much of it is in there? Now, the what's in there is a pretty well understood problem. Based on the energy spectrum of the radiation, you can look up which peaks correspond to which isotopes, and you can guess pretty closely what types of materials are contained. However, guessing the amounts of materials is a little more difficult, or maybe it just hasn't happened, or it's still being worked on, I should say. So, so if you have the crate, though, and you have a sort of a blob of materials in there, we're not looking for an exact replica of what it looks like. We're looking at vague, sort of, not vague, but a general idea of what things look like. So we're going to assume that it's a spherical mass in there, since we really have no better assumption to make. And the problem that I have posted here is suggested by Jeff Favorite in 2004, and it consists of uranium central sphere, and then there's a void region, and lead and aluminum shielding. And the uranium is emitting gamma rays, which get scattered through the lead and aluminum and shielded through the lead and aluminum. And the idea is if you stick a detector somewhere right here, could you, without being able to look inside, could you determine what these measurement values are, which those radial locations are? Now, there's a number of different methods available to solve this. One of the most successful ones is Levenberg-Marquardt nonlinear least squares method. And there is an advantage of that one that, unlike a lot of the other methods, that you do get an estimate of the uncertainty of the model parameters at the end. But as we're going to see at the end, it's a rather crude uncertainty estimate. And so to get a better estimate, we could use Bayes' method. So I apologize to all those who are experts in Bayesian inference. I don't really consider myself an expert, but I think there's probably some of us in the room that aren't really that familiar with it. So just quickly, it's really an intuitive process where you start out with some initial state of what you think something looks like, and you get data in, and based on that data, you reformulate your state of knowledge of the system. And Bayes' theorem is simply a way to do that formally, where you phrase your state of knowledge as a probability distribution function. If you're interested in learning more about that, James mentioned this yesterday. The Inverse Problem Theory book by Tarantula is very helpful, I think. So I'll skim through these next two slides because James did a nice job talking about them. The essential things is we have two main categories. We have the model parameters, which I'm going to call them alpha, and the measurement or the data that we're going to have in another category, represented as R. And then we have a covariance matrix describing those. I think one difference, maybe a slight difference with what James was describing, was we have a cross term to capture possible interactions between, possible correlations between parameters and responses. So in order to maximize the posterior distribution, we want to minimize the Q functional, and we're going to use a Gauss-Newton iter procedure, just as you've heard already several times. And we're going to compute the linearization with adjoint, with a set of adjoint solves, so that we have the full derivatives. So that's kind of the brief synopsis of the Bayesian methods that I have used. Getting back to the problem now, and I'd like to emphasize this slide because there's a important note about the difference between what you're computing, your forward model, and what you're measuring. It's called a model for a reason. You're not going to get exactly the measurements, and so this is really the key to understanding how to characterize that difference. So the alpha vector is the state parameters, and I'm calling the thicknesses delta rho, and we'll take the logarithm of that because, number one, it eliminates negative thicknesses, which are unphysical. And secondly, it gives a broader distribution. So instead of a normal distribution, it's a log normal distribution. For the prior distribution, which we're going to assume at the beginning we don't know very much about, it's nice to be able to make those, that bell curve nice and flat. So the key here, though, so this is kind of the obvious one that we would include. The key is to add uncertain parameters that also affect the model, but maybe aren't as obvious. So for instance, the total macroscopic cross section, which is just a materials property, we don't know that exactly. We have a pretty good estimate, but we don't know it exactly. So we want to include that in our model, and hopefully that will help to describe the model to experiment discrepancy. So the problem starts out quite simple, 4 components. If you add the total cross sections, it's about 10 to the 3. If you add other of the cross sections, it would grow even more. But for now, I did just the total cross section. So this is the key to describing the model mismatch. Now, when I go to get the cross sections, they're a function of energy, and they're tabulated in a pointwise fashion, like the green line. And I need to bin those into groups for the multigroup calculation. I'm going to use for the forward problem, or for the inverse solver, I'm going to use discrete ordinates multigroup calculation. So I need to bin those data into these different steps. And obviously, when you have, if you're at a continuous place, you're still clearly going to have an error. At the jump discontinuities, it's going to even increase the error. So clearly, we have some errors in the multigroup cross-section. And that's just coming from the spatial, or from the energy discretization. And so what do those errors then do in the forward calculations? So what I'm showing here is, assuming that we do know what the thicknesses are, we can compute the actual detector measurements, and we can also do our measurement. In this case, I'm using a measurement that was not really a measurement. I'm using Monte Carlo, which is a separate numerical approach to solving the forward problem. So the key is, though, that those are two distinct approaches, and there's going to be discrepancies between the two. And I do scale the error of that experiment based on counting statistics, which would be what you would do in an experiment. So it's at least comparable to what an experiment would be. And the idea is that we have error bars on both the computed and the experimental values. We'd like to have those error bars overlap. Obviously, that's what we would like. And the bottom show a plot of the relative error bars on the calculations, the experiment, and then the difference between the calculation and the experiment. And you can see, for the most part, we'd like those to be of the same scale. And it does seem like, for the most part, they are, with the exception of maybe at 0.2 MeV and 1.2. Those two groups seem to be giving the most error. So we have a decent chance of solving this problem, in other words. So moving to my last slide, I plug all this in and forget that I know what the right answer is. And focusing on the top row, I have a prior distribution that's quite wide. Say for the 1 sigma window, I'm going to go from 0 to 20 centimeters, and it's asymmetric because that's linear, and we're solving in log scale. And I'm using the same window for data assimilation, DA, or the Bayesian method, and Levenberg-Marquardt. And so I plug all those numbers in, turn the crank, and out comes the posterior distribution for the red, the Bayes results, and the uncertainty estimate for the Levenberg-Marquardt. And I'll just draw a few conclusions, and then I'll finish up. So first, the dots representing the mean do a pretty good job of getting close to the green lines, which is the truth. And the error bars on the Bayes method do a pretty nice job of enveloping, in all cases except the aluminum, which is still pretty close, just outside the 1 sigma window. So that's the first observation, that it does a pretty nice job of estimating the uncertainty. The second observation is in the void row here. We see that we've estimated somewhere between 0 and 15 centimeters. That doesn't really sound that great. But if you think about what happens in the void, pretty much nothing. And so it's not surprising that we have very little knowledge about that thickness. And then finally, the LM method does a nice job of showing what happens when you don't include these extra uncertainties in the inputs. So, for example, the total cross-section uncertainties. So say you were interested in how much uranium was there. If the critical, the critical radius of a uranium sphere was 8.4 centimeters, and you said, oh, we're 8.0, well, we're way, we're fine. Well, and it looks like the uncertainty is quite low. That's misleading to someone looking at that. So yeah, in conclusion, I hope that I've conveyed the importance of Bayes' method in estimating the model mismatch between computed model and experimental data. Thank you.